I'm Stephen Frederiksen.
I'm Puvanai Avakul.
I'm Zachary Yee.
So our scenario is we have an area that is aerially mapped. We know where all the obstacles are already. We have a system of 3 rovers that can be deployed in that area. All of them can navigate around all the obstacles that have already been mapped.
For the individual project responsibilities, Zachary worked on the distance sensor, Stephen worked on the rover navigation and GUI server, and Nicky worked on the motor calibration and movement and worked on the IR sensor.
The first rover is a simple rover that uses the data that's stored on a server to navigate the area. It's simple, it has no external sensors to detect objects. It only has a communications module that can communicate with the server and get map data.
So the second rover is a seeking rover, and this rover has an IR sensor that can detect any objects within 1 centimeter. So this can be used to confirm hiding rover position or any objects on the map.
This is the map rover. Like the other 2 rovers, this rover can go anywhere on the map. However, it has a stepper motor and a distance sensor. The stepper motor moves the distance sensor around in 360 degrees so that it can detect obstacles on the map.
The RNXV Wi-Fi module is a shared component between all rovers. The primary function of this module is to send and receive commands and data from the server.
I'd like to talk a little bit about our team's message format. All the messages between the microcontroller and the server uses JSON string with a payload that contains 3 fields: the command, type, and data. And for integrity and synchronization purposes, we have the checksum of that payload and the sequence number of the message attached to that JSON.
The VL53L0X is the distance sensor used only on the mapper rover. It uses I2C to communicate with the microcontroller. It is a very accurate distance sensor that can measure distances between 3 centimeters and 1 meter. This sensor is used to detect new obstacles on the map. By spinning this sensor on the stepper motor, the system can be used to detect obstacles around the mapper rover. This sensor has a very lengthy initialization and calibration stage which takes several seconds and must be performed before getting any distance data from it.
Control module. This module, its functionality is mostly concerned with turning the stepper motor and allowing the user to control that turning. So it interprets commands from the user to actually start a timer, which turns the stepper motor at a specific rate in a specific direction. Stepper motors are pretty easy to control. It's just sending a sequence of 4 different 4-bit numbers through the output pins that connect to it, and if you do it in the right order and at a slow enough frequency, then the stepper motor will turn as you expect it. You can reverse the order of the numbers that you send, and it will also reverse the direction of the motor.
For the IR sensor, it is a short-range sensor that detects objects within 1 centimeter. I have the sensor on a breadboard and connect the output signal to one of the analog pins on the microcontroller and configure the ADC to sample every 1.5 milliseconds. As for our design requirements, the sensor was able to detect other rovers and objects within its range.
The server is the main bridge between the user and all of the different PICs. Most of its functionality includes passing through different command and statistics messages between the user and all of the different PICs, and then also actually fulfilling requests where it can. So this includes database stores and loads. Most of the GUI's functionality is just reflecting the different state variables that are on the PIC. These are sent up from the PICs via the server, and once the server gets the specific messages that correspond to state and error changes, then it sends them out through specific UDP ports that are correlated to each of the PIC's TCP ports. The GUI is then listening on these ports. It parses the different messages looking for keywords that correspond to the different types of messages that can be received. Once it gets a message, then it then parses it, gets the values that it needs, and updates the visuals on the GUI. This includes the map itself changing, the pick's position and destination and radar values. Additionally, it takes into account the different error variables that can be sent up. This includes the message rate as well as different error rates that can be sent. The GUI itself is organized to be mostly a observation tool. Most of the visual space is dedicated to actually looking at the map and the rover's position on it, and in the mapping rover's case, the actual radar output of its radar functionality. And additionally, the statistics such as error rate and different message rates. The last piece of functionality of the GUI is the actual control interface. This includes manual corrections for navigation and other predefined messages such as sending the destination, correcting where the rover currently is, starting and stopping navigation, and in the mapping rover's case, starting and stopping the scanning of the radar. Additionally, it allows the user to send any arbitrary command. If they know all the different commands that can be sent, that will be interpreted by the specific PIC that they're trying to communicate with, then they can send any of the commands through the arbitrary command button. Additionally, the interface itself is organized into 3 tabs corresponding to the 3 different rovers.
This is a small demonstration of the stepper motor and distance sensor combined. The moving of the stepper motor and distance sensor reading are only done when the rover is not moving, as displayed here. And on the right is what appears on the GUI after the system has gathered data around the mapper rover. Here is a full demonstration of the HIDAR rover navigating on the map. Stephen will talk in more detail about the navigation module.
I also worked on the navigation module and all of the different PICs. This module is basically the main state-keeping tool of each PIC. Most of what it does is keep track of the current map where all the different obstacles are supposed to be, in addition to the rover's position on that map and where it's going, as well as its current path between the 2 points, if there is any. The path is calculated using a dumbed-down A-star search, essentially making it a breadth-first search, but this one is highly optimized for space and memory efficiency. Everything in the algorithm is statically allocated from outside of the function itself, and this allows it to be fast as well as have a very low memory footprint. The navigation module, most of its functionality is dedicated to actual navigation around the map, keeping the state variables that are necessary for this and interpreting commands from the user to facilitate this, such as setting the destination, setting points on the map to be obstacles or not, and also starting and stopping the navigation. The rest of the functionality of the navigation module is essentially just facilitating state changes such that from the user. So this is loading and storing the map into the database and from the database, as well as sending statistics between the 2. The last piece of functionality of the navigation module is interpreting the path generated from the A-star search into actual motor commands. So when you're going between all the different blocks on the map, converting that to left-right turns at different power levels and different degrees, as well as allowing the motor to go forward and backwards rather than only going forward and having to do 180-degree turns every time it needs to change direction.
This is a demonstration of the Seeker rover confirming an obstacle on the map. In this case, the obstacle is the HIDAR rover. The rover has to get relatively close to the object to detect it.
The rover movements, they are not 100% accurate. When the rover is moving at full speed, it always stops 1 to 2 centimeters beyond where it's supposed to, and this is because the rover has some braking distance. But by reducing the speed to 50%, the braking distance is reduced. Some other issues we have are that the rover shifts slightly when it moves, so it doesn't go quite as straight as we want it to, and that when the rover turns, they are not as accurate as we want it to be. And this is because I am reading the motor pulses from one of the motors, and not all motors are calibrated to the same exact speed, so one motor might be rotating faster than the other, which is why we had to employ some manual corrections from the server.
In the case of the distance sensor, as I mentioned before, the sensor takes several seconds to initialize. However, this was solved by the rover sending a complete initialization message to the server. Also, if the sensor is operating for a lengthy period of time, roughly 4 to 5 minutes, the sensor will stop working for an unknown reason, but it is assumed that it is a hardware error on the sensor. To solve this, the microcontroller can send a reinitialization to the sensor, and if this does not work, we can manually shut off the rover and turn it back on, and this will definitely solve the problem. In this project, we also failed to implement one of our specifications, map generation. The system originally was supposed to generate a map with no previous data with the map rover. This specification was scaled back because getting all functions to create this feature was deemed too complex.
As for improvements for the rover movements, instead of relying on manual corrections, we could implement a dynamic motor correction by reading from both of the motor pulses. This way, we can find out when the motors are rotating at different speed and adjust the motor speed accordingly so that they rotate at the same speed.
The project could also have improved by using different sensors. The distance sensor had a long startup time, could fail, and using I2C with a PIC32 microcontroller caused massive issues in integration. By changing the distance sensor with something more robust, the system could operate longer without a reset. Also, by using a sensor that relied on something like UART communication instead of I2C, we could more easily integrate the systems. The IR sensor had a very short range. Simply by using a more powerful sensor, we could detect obstacles like another rover more easily.